Thank you. Now I have a new tool to progress my slide. Hope it'll work. Oops. So my topic is vision. What is a vision? Vision is, here's a scene, and we have a device called camera, and we take data called images. And then what the vision does is from image to figure out what the scene is. Now, it sounds as simple, but actually, obviously, it's a very difficult problem. As you see here, guessing the reality from projection is a pretty tough problem. Now, computer vision is indeed one of the earliest problems in artificial intelligence. As you may know, it started in Bloch's world, hand-eye project, and vision program, computer vision has been tried from early on with a quite intensive effort. But nonetheless, it turns out to be very difficult. And there's a very well-known episode that Minsky said that vision must be very simple. You, a graduate student, can solve as a summer project. And it turns out it's so difficult that even after 40 or 50, actually more than 50 years, we are still working. And I'm happy that it has been solved because I made a career on it. By the way, actually, when I asked Marvin about this, he said he didn't mean that. But anyway, that is a known episode. Oops. It doesn't. Now, why is it difficult? Well, the one is the sheer number. Even the VGA video produced 20 megabytes per second. When it comes to high-definition TV, 160 megabytes per second. So we have to process this much data. Indeed, it is often said when compared with speech, vision is two-dimensional, we have a lot of data, and so forth. And that's true, even though I'm not sure the sheer number is that a difficult thing. Now, as to the number, there's an interesting fact, simple fact, I say. A large image consists of a large number of small images. Now, learning is very popular today, so if you're shown one high-definition TV image, 2,000 pixels by 1,000 pixels, then in it, now I have a habit of showing let me see, is this? In it, there's a 10 by 10 image here, and the next and so forth. So there are 1,090 positions this way and 990. So in total, you must have seen roughly 2 million 10 by 10 sub-images given one high-definition TV. So by just seeing one image, you must have learned 2 million 10 by 10 images. That's a lot of learning. But there's another simple fact, I say. That is, let's ask how many 10 by 10 images exist. Now imagine one pixel is made of 8-bit black and white pixel, not even a color, 8 bits. So 256 different images of one pixel image. So if it's 10 by 10, then 200 power of 10 by 10, which is 10 of 240. Now let me prove how big this number is. This number is far bigger than this very important number for human being, which is, imagine, for safety, human being was born 1 million years ago, maybe a little later, but say, just for safety, 1 million years ago. And even day one, imagine 10 billion people were living on the earth. Probably only 500 people at that time. That's my guess. And imagine they are individually watching every day, every hour, every minute, every second, 30 frames per second, high-definition TV. Each of them is watching different channel, not the same channel, different channel. And in total, human being must have learned 10 of 31. That's far, far smaller than 10 to 240. Now you might say, no, the world, China, there are many more people. Maybe so. Well, let's make it 11. You may say, no, human eye is not 2,000 by 1,000. It's worth of 1 million pixel by 1 million pixel. Maybe so. That will increase this number 12. But that doesn't make this number nowhere near 240. So I have proven a very important point, which is humankind has not yet all of 10 by 10 seen all of 10 by 10 images. I call it Kanada's theorem. By the way, I have never seen anybody yet who could refute my theorem. So I believe this has been proven. So this means that this implies that we need actually a fairly bold assumptions to solve any vision problem. So that is actually the meaning, in my mind, the sheer, why it doesn't, okay, number aspect. But why vision is really difficult is actually more than that. One is 2D, 3D degeneracy. Image is a projection. So three-dimensional world is degenerated. So basically we're asked, 2 times 0 is 0. What was the original number? It's impossible in a sense. And, well, you may say that, well, from this, for example, this one, the world is 3D, picture is 2D. From 2D, we ask, which of these buildings are farther? Now, we may say, it's obvious, this building is farther. And we ask why? Because that building looks smaller. Nothing wrong to have a small building in front of a big building. You may say, oh, no, this building is occluding this building. Nothing wrong to build inverse L-shaped building is built. So actually, this inverting projection is theoretically, obviously impossible. Now, another difficulty is, doesn't work, is signal compounders. Pixel value is the result of compounded physical phenomena. For example, this pixel from you this is dark. That is because this cloth is dark. This is wider than here. That is not because the cloth is wider, but because more light is on. And as a picture, you can't tell which was the reason. And somehow, we should be able to recover that. And that is obviously a very tough question. Context, which is artificial intelligence's favorite topic. When you ask, what is this? And then people say, car. Now, you ask the question, why is this car? People say, because it's on a road. Now, in this, obviously, the context is playing a big role. Because if you remove all of the context, this is the thing. It doesn't look like a car. And for sure, this context, which is the road, is making that small thing appear as a car. But if you ask, then why is this a road? Then most people say, because there's a car on it. And, well, that doesn't help us to solve the problem. So that is the kind of problem that we should discuss, we should attack. Oh, I hate this. And so, in summary, computer vision's fundamental difficulty, apart from a sheer number, is this cyclic dilemma in one-to-many problem. As I said, from projection, recover reality is one to many problem. And in that, we have many chicken and egg cyclic problems, such as distance. Once we know the size, the real size of the object, of course the appearance will help you to know the distance. But if you don't know both, neither, then we have a kind of cyclic dilemma. So is the case of occlusion. For example, if we know my hand occludes my face. But in order to do that, know that, you probably have to know this is my face. Otherwise, you cannot tell this is not part of the face. So that is, and another thing is manual coding. Early on, the typical approach in computer vision was what I named, let's program what I think I'm doing. Whenever given a picture, we thought, oh, what is tree? And they say, oh, tree is green thing on top of brown thing. So we wrote the program, what I call, let's program what I think I'm doing approach. And everything was like that. But unfortunately, each of us is a vision expert, but does not know how we're doing it. So that approach didn't work as well as we thought. Search explosion is essentially when we turn this cyclic dilemma to a search problem, which we should, then the search tends to explode very quickly. And computers have been too slow for that. And a very important thing, which I think people have forgotten early on in artificial intelligence, is the lack of understanding how to use physics in vision. I think the physics has been neglected for a long time in spite of the fact that physical process, optics, geometry, etc., and noise is indeed dominating how the picture is taken. And so those are the reasons why the problem was so difficult. And nonetheless, I think we have made some progress, and I'd like to go over a little bit of progress by using only my and my CMU colleagues' work. Sorry if I don't use your work, because I couldn't collect all of the examples, but I collected example from our own work. So let's go with that. So face recognition. 40 years ago, this is my PhD thesis, 40 years ago. And today, it seems that my usual joke doesn't work. I think when I give a talk, and always I say, probably none of you were even born when I wrote the PhD. But here, it seems that many of you were born or even before me, so it doesn't work. But anyway, 40 years ago, this is my thesis. And can you tell? It's interesting. 40 years ago, when we processed one image successfully by our program, we could write a paper, and it passed. And if we processed 10 images, we proudly said, with a large-scale experiment, we have shown X, Y, Z. Now, at that time, one of the proudest thing I had was this program was actually tested with 1,000 images at that time. And, but nonetheless, it's only 33 people, about 75% of recognition rate. But since then, myself, actually other people have done quite a bit of face. This is our work, detection, which we use every day now on your cell phone and camera. And this is 1996, 98 time. And actually, it's pretty good. Today, this is very common. And if you look at it, of course, detection, we say face detection. Precisely speaking, this should be called face image detection, because obviously this is not face. See, this is face image. The program does not know that. So it's proudly detect that as a face. And know that as not a face, but a face picture is, of course, pretty difficult task. And today, the more difficult and common problem is called alignment. That is actually no individual component in the picture. And we have done some progress, made some progress, and the program is actually available online. If you send your picture, we process, and you'll get it back. And it works pretty well. And I think a Chinese student sent in a very beautiful picture. It's so sent in. And the Japanese person, obviously, a very meticulous. He wanted to have what I call stress test of our program. And this is what the guys sent, like this. And it took 2 hours to process this image, about 500. Actually, this picture is much bigger than this. And it successfully could do that. And then, of course, in real world, it's actually interesting. Many people do extreme expression. And this kind of program uses so-called knowledge, how the face, the parts aligned and so forth, and position relationship, size relationship, and so forth. And these examples really violate some of the very common ratio, for example. This guy, the distance from here to here to here, is usually about the same from here. This guy is about twice as big as this one. So it's not easy. Because if you allow them to be a legitimate face, then a lot of faces which are not legitimate will now recognized as a face. So you have to deal with that problem correctly. Finally, I think we have a pretty good alignment program which actually does precise all pose, three-dimensional, and occlusion robust, in the sense that all of the occlusion. And not only that, the result, I think I'm fairly proud of it, because it's just like almost hand-generated. And more than that, it actually knows the occlusion. So when you do this program actually doesn't output this portion. Because program knows this is not a face. This part is not a face. Program knows this part is not a face, and so forth. Program knows this part is not a face. Therefore, it doesn't try to output eyes and so forth. So I think the occlusion is, in this simple example, is we are getting handle on it. And face recognition today is actually amazing. And if you look at this progress, last 5 or so years, actually, human recognition rate, given this type of image, which is full image, face itself and background, is about 99.2. I think computer is actually getting there. And if this rate is the case, then you see within 1 or 2 here, this rate will surpass the human. And that's where we have today, and I think it's getting, oops, will you go back? Yeah. So face application everywhere today. Camera, cell phones, internet security. And as I said, computer face recognition is as good as humans. And indeed, if for most serious applications, human performance, computer performance is actually better than human. For example, given a database of 1.6 million mugshot, recognition rate is as good as 95%. You cannot do it, because we cannot look at 1.56 million people, let alone even 100 people. I'm not sure if we can do it correctly. So face is pretty under control, and more is coming. And this is one of the programs that we have, which called Obama Speaks Japanese. And we create Obama's face, which is easy. Movie industry does that all the time. But the point is that input is done completely passively without putting any dots. more,
表情を
so
理解
far
する
more
というのは
dots.
なかなか
And
難しい
I
こと
think
なん
we
です。
can do it.
いろんな
I'm
顔があり
saying
ますし、
the computer
顔が
vision,
こう
face recognition is difficult.
いろんな方向に動きますし、
And,
表情というのも非常に大
Obama
です。
endorses
しかも
my
表情は
statement.
すごく大げさに
Thanks for him. The next topic I'd like to talk a little bit about is multi-camera vision. 20 years ago, early 1990s, I started multi-camera research. And I had a strong conviction that the stereo should use more than 2 cameras, in spite of the fact the human has only 2 eyes. I think that is accident. I think we should have had more eyes. That's my strong belief. So we started 2, 3, 4, and so forth. And then we built 1992 5-camera system, 256 by 256 by 8-bit depth image in 30 frames per second. That was one of the earliest machine, which amazingly consumed 5,000 watts. 5,000. It's hot, actually. When we turn on, the whole room didn't need any the heater. It was so hot. And then we built 51 camera system here, circa 1995. At that time, we didn't have enough bandwidth to take all the 51 cameras input into computer in real time. So what we did is we bought 51 VCR, videotape recorders, and in the corner. And all these cameras were synchronized and time-coded each frame. And after the experiment, we took video out and put it in a digitizer, another one, digitizer, and because each frame is time-coded, we know which frame on this tape corresponds to which tape on this. But can you tell? I can tell you, when you have 51 VCRs, even doing the experiment is very tough. Because when you start, you have to push 51 start buttons. My students complained, "Professor, you are a robotics professor. Please develop robots to push the button." I said, "No." And he asked, "Why?" I said, "Because students are a lot cheaper than robots." So anyway, that was the story on that. But by the way, I had a strong conviction that large number of cameras is common. When we wrote a paper on the 5 stereo camera, it was rejected. And the reason was, this camera, which uses this stereo system, which uses 5 cameras, will never be used in the world because it's so expensive. That was the rejection. And it says, this can be built only by Takeo Kanade, who has so much research money, but not in real world. This is a true story, indeed. That was the rejection letter that I received. And it's so funny that the world changes so quickly. And then from that, inside of that dome, what happens can be digitized. I call 4D digitization because X, Y, Z, T. And once it's digitized, you can actually synthetic court, and you can see the view from anywhere. And based on this one, we did some system which is named Ivision by broadcaster CBS, which is used for Super Bowl broadcast in 2001. You know movie Matrix? I haven't seen it myself, but I was told it was, the main character jumps and you can see spin around him. And that is made this way. all these dots are cameras. And at the center, which all these camera focus, the actor performs. And at the right timing, all the cameras take picture at the same time, and they are concatenated. As a result, you think as if the time is frozen, you're spinning around it. So the idea is to do the same with the football field. But the football field is large, and of course you can't tell where the interesting thing will occur. Therefore, each camera is replaced by a robot camera, which actually track the particular point. And this is what we got. Would you play?
Now, during today's coverage of Super Bowl 35, CBS Sports will introduce a new technology called Ivision. It provides panoramic coverage similar to the special effects in the hit movie The Matrix.
Broadcaster. I met him. He's a very nice guy.
30 robotic cameras have been mounted on the scoreboard and
He's
all
a
along the upper deck
robot camera.
of 7 degrees. Each camera feeds into one.
And these are actually storage at that time. Today, probably this
The
small.
images are then computer calibrated
And
to
this is the monitor
instantaneously
system.
show any spot on the playing
You can
field
see it
from
like
all
this.
angles within the camera's 220-degree range. Professor
And this is
Takeo
me.
Kanade of Carnegie Mellon with
When I
designing
was
the
young.
software that blends 30 cameras into one dynamic panorama.
This is a gigantic robotic system. You have to have perfect idea of the direction, position of the cameras, and the relationship of the amount of zoom, amount of focus to the command that you give from the computer. And that is one of the hardest jobs.
Players out, takes the pass, cuts back inside, across the 40 to about the 41-yard line.
All right, here it is. This is an example during the warm-ups taken just a moment ago. The pass from Banks to Davis, and look at the way it can whip around. We're all looking forward to it. By the way, it can be used in instant replay situations in the case of a challenge.
We will talk from time to time tonight about Ivision. If you're wondering what it is, this is what it looks
So
like.
this is how it works.
Quarterback, he drops back. Look, he sees a big lane. Look at that big lane, so he steps up into it. What always makes it easy for a quarterback is to have a clean line of sight. Watch Trent Dilfer, nice look off. Looks to his left, and nobody in front of him. Look at that nice lane. He can see the receiver down the field. And what a throw.
Yeah. So I usually say that I'm the only professor that has ever appeared on Super Bowl.
Brian
And
Billick
there's a
looking
lot
at
of
his
story
offense to
behind
put a
this.
nail
But
in
I'm
the
not
coffin
going
right
to talk
here from
about
the
it.
3-yard line.
Now, so today, multi-camera technology are used everywhere, indeed. Our system was 51 camera system. Super Bowl was 33 camera system. There are 200, 500. There are a lot of them today. And entertainment, as you know, multi-camera system that will allow you to get the picture everywhere in focus picture. And if you can actually, if you have foliage, tree lines, by having a multi-camera, you can actually see through for some military applications. And surveillance, we know that is common. And today, actually, we are actually looking at even a larger number of camera calibration. This is the designed 1,000 camera system. Each dots in this room, a camera. Today, we have actually 480 combined. And with this, certain performance can be taken and digitized and can be modeled. I think the guy is spreading the papers. We can actually do a lot of modeling of events inside. Let me see. So one of the things that we are looking at is to use this kind of system to study human communication. So for example, we have 2 rooms we're going to have with high definition, very high display. We are looking at about 8,000 by 6,000 display. And you are here, and you're thinking that you're talking with a beautiful girl, but actually you're talking with me. And this one is actually synthesizing, converting the reality, and so that I can control the timing, the manner that the person smile, nods, and see how you change your reaction. In other words, when you say, I like him because he agrees with me, is it because he or she looks actually agree with you, or the way you say the same thing? We can change it as we like, and that's the kind of thing that we're looking at. Autonomous driving. 30 years ago, this is what we started. It was initially was about 1 centimeter per second. It's barely moving, and this is CMU's near, and this is the ordinary store. And when a child comes out, car stops. And the story is that the guy, that's the child, is a son of a programmer who coded to stop at the dangerous situation. And actually this system later, 1995, so it is what, almost 20 years ago, we actually did No Hands Across America campaign 20 years ago. So we drove this 3,000 miles from Pittsburgh to DC, 98% of which was computer vision controlled, 20 years ago. It was very interesting, but not 100%. So it's not usable today if it's not 100%. Indeed, we are sitting at the driver's seat and not holding the steering wheel like this, just in case you can hold it. So actually it's more tiring than driving yourself. That's what we had. And another interesting story that I have is that you know Jay Leno, the famous comedian? He actually used this system when this car was driving across America. He uses, newspaper article as a source of joke. And he said, here is an article, he said. Carnegie Mellon University's researcher developed autonomous driving car, which allows you for the first time to take your hands off the wheel and drink a coffee, read newspaper, or makeup. And he said, why is that world first? In Los Angeles, people have been doing that forever. That was his joke. And so that was interesting, and we actually had fun. Now today, this is 2007. This is our CMU's Red Whitaker's work. It actually had a first prize. And this is complete autonomy. Even a human, for safety, is not on the car. And it was very interesting that the progress is being made in about 12 years. So today, driving assistance is with us. Autonomous driving is in sight. And the vision-wise, a lot more coming in a sense of robot is getting the genuine understanding of what is going on. So far, all the program that has been developed is very limited to understand the lane, where a person or other car is, not the total understanding of the scene. So I think the Carnegie Mellon University's researchers, Munoz and Marshall Hebert, they're actually having a program which, given this road scene, not only know where to drive, but also other things. scenery understanding, which is indeed the real sense of driving, because by that you can guess where the person might come out, or this is a child, therefore it's more dangerous, and so forth. Possible case of change the action and so forth. And that is coming. And what we have today, one of the things that I'm interested in is new augmented reality. And let me talk about this for the last topic, which we are doing right now, which called new augmented reality, that combines illumination, projector, and vision in one device and enhance the vision, human vision. So in a sense, it's augmented reality. But it's not augmented reality of what we tend to hear. That is, you have a cell phone and look at the thing, and the cell phone says, oh, this name of this building is such and such. It's called augmented reality. I call it, no, it's not augmented reality. It is the augmented display of reality. Reality is not augmented, you see. Display is augmented. What we are interested in is augmenting the reality. So what does that really mean? So in driving, this is rain. This is what you get. The rain looks very white and blocks your field of view. It's annoying. You know why? Because the rain is, raindrop, and the same is true with the snow, are highly reflective. They act as a convex lens and collect the light and return. That's why it looks white. You know? In other words, headlight hits the rain and returns. So, what we should do is, when rain comes, look at where they are and control the beam in such a way that the beam will not hit the rain. Then you should not see it. Okay? Now, you may think that's a silly, but actually it's not that difficult. Imagine your projector and camera is placed at the same place. So the projector's line of sight means the direction of the shooting the light is the same as returning of the camera. Okay? So send a light very briefly, take a picture. Then the rain should become white dots. And imagine that we can process that image and know where the rain dot is in the picture with 0-second delay time. Then what we should do is turn off the projector. So we change now the headlight to projector. Basically, that projector, the same projector. Turn off the beam that corresponds to the dots. Okay? But actually it takes a little time. So by the time we are ready, probably the raindrops will be a little lower. Yeah? Therefore, what you should do is turn on the lights above it. Side safe. This is safe. Here is very safe. Very safe. Very safe. Very safe. Almost safe. Almost safe. Now this place is maybe not as much, because the wind may make this way. So if you shoot the light, it may hit. Okay? So that's the strategy. And indeed, if you take a picture with 1 millisecond, then rain for sure looks like a dot, because the rain is about 10 meters per second, no faster than that. Okay? Okay, so as soon as I got the idea, what you should do is we have projector, indeed that projector, the same projector, and put the camera with half mirror and processor in between. So we modify the projector. By the way, projector works, most of the projector, about up to 60 frames per second. That is only because the need is that. The projectors, the mirror, the small mirror, goes as high as 2,000 frames per second. So we modify it so that it works. And put that in together with the camera, with a half mirror. By the way, the brightness of the projector is about 4,000 lumen, which is even brighter than the headlight of ordinary cars. And we built our own headlight and put it on a car. Oops. Put it on a car. Then you see, rain disappears. Oops. Snow too. But this is not real snow. This is a snowflake. And in a slow motion, you see, it's easy. In slow motion, this is about the speed that you have to deal with. In computer vision today, it's not a difficult task. So once we do that, oops, that's really, I hate this. Will you go back? Yeah. One back. One back. Yes. We can think of a better, easier one too, which is up beam, low beam. You see, when you're driving, you're supposed to, up beam is easier to drive, but when the car comes in from front, you do the low beam. Because the high beam will make you, the driver of the other side, momentarily blind. Do you know that period of momentarily blindness takes longer for 55 years older? About 5 times longer, 8 times longer than 16 years old. So many of you are in problem. So what we should do though is you don't need to do the low beam. All you have to do is to turn off the beam which corresponds to your eye. Then you don't think it is a high beam. No? Let me see. This doesn't work. Yeah, so like this. So this will make always up beam headlight. And indeed it works. Oncoming, this is the other car. It doesn't look like a high beam. This is your car. It's always high beam. In fact, if you don't, we turn on and off this is high beam. See, if we don't make that capability, if you turn off that capability, it looks like a high beam. But if you turn on that capability, it looks like a low beam to you. But that guy is always high beam. Okay? So I think, sorry, I actually designed to be about finished in time, but the rear view is the same. Rear view, when the guy comes from behind, it's annoying. So all you have to do is turn off the beam, which corresponds to the rear view of the car in front of you. And then the guy in front of you can actually see you clearly. Okay? Like this. But you always high beam. And if you have actually combined with the radar, with the camera, then detect a person in the fog. Now this is a tough one. Somehow we have to let the person know there's a person in the fog. Now, showing this doesn't help because then when you're driving, you have to look at the display. That's more dangerous. Okay? You have to look, it appears to you that the person is visible. Now, one way is, of course, is to send obstacle out spotlight. But since it's a fog, it may or may not work. So one possible idea is we have actually more projectors on the car and converge the beam so that that particular position will get the higher one. Okay? Now, for that, you need a baseline. And the car's baseline, which is about 1.7 meter, may or may not be enough. So we may have a high pole like this, and then we may be able to focus on the point. Or eventual solution is put electrode on your here, and the processed image will be fed to your eye, then to your brain, then you'll see a person through the fog. Now that's a futuristic idea, and you may or may not want that solution. But anyway, so as you see, this is not an augmented reality of display. This is real augmented reality. So finally, sorry to overrun, I think future, various points, I think it's obvious, ubiquitous, sensors, low power, processors, real-time access to internet, and so forth will actually bring us a new brand of computer vision, which is somewhat different from traditional sense of computer vision. That's what I wanted to say. Thank you very much.